Today I want to look at arrays, and that's interesting because arrays really touch this border of what is expressible in a programming language itself and what has to be done under the hood by the runtime. And many languages take a different trade-off there. Let's maybe draw some stuff. You can think of most data structures, they kind of depend on even simpler data structures. For example, at the lowest level, we have something like pointers and addresses, and you're implementing something like memory allocation and managing like where do we store what in memory. Then on top of that, you can build something like slices, memory regions where the same item is stored multiple times, or maybe just some bytes are stored there, or buffers. And then on top of that, you can design maybe like typed versions of these. So I'd say that these are just untyped, just slice of bytes, maybe slices of bytes and buffers. And then on top of that, you have something like arrays or typed slices, or however you might call that. And then using those, you can implement array lists or like growable lists in general. These are all data structures. Some languages have some of these, others have others. But the interesting point is, where do they draw the line? What does the language automatically provide? And what can you build from within the language? For example, in JavaScript and I think most interpreted languages, these typically dynamically typed interpreted scripting languages like JavaScript, but also Python and Dart and stuff like that. They have the border up here. So these kind of growable lists, they are built into the language. They are not part of the standard library, they are a language feature. On the other hand, in Rust, for example, Rust provides pointers, I guess, and bindings to the C malloc. So the border is somewhere between there. But also like slices, at least typed slices, are part of the language. So I guess that's kind of like that. But something like growable lists, called vectors in Rust, they are entirely implemented in the standard library. That's not a part of the language. And it makes sense that different languages choose different boundaries for the language, because some languages are memory safe. That you don't want to allow the code to deal with pointers directly. But on the other hand, if you want to allow more control over performance, then it really makes sense to allow you to write your own data structures that have that have a very deterministic, predictable memory layout that you can optimize. So where do I want to put my language in here? Where do I want to draw the border for Plum? And I think let's just go through some options. So I don't want to... Plum is garbage collected and memory safe. And also data is immutable. So these here are definitely part of the language, pointers and malloc. Let's maybe add a different layer for that. Maybe even yeah. These are part of the language. Then the question is, I think I do want a way to express something like multiple items in memory next to each other of the same type. Because that is a very fundamental data structure that many types need to be efficient. Maps need that, array lists need that. If you create something on your own tree data structure, I don't know, you might want that. But I still want to go. I want to go as low level as possible, while allowing you to write memory safe code. So I want array lists to be part of the standard library, not to be implemented in the language itself. I think the correct way would be to have the border here. You know, I know the names are kind of wishy-washy at some point, like size of bytes, buffer. I kind of use these simultaneously. Same with these. But I think I want to provide, as a primitive in the language, some sort of array that represents multiple items of the same type in memory next to each other. And then on top of that, the standard library builds growable array lists and maps and what have you. I think that makes sense. However, Plum is also an immutable language. That means that semantically, data can never change. For example, if you have numbers that make sense, like a 4 can never change. A 4 is just a 4. But the same is true for lists. The list push function will just take a list and an item and then return you a new list with that one extra item. And the question is, how can I implement that efficiently? What you would usually do in such cases is have some sort of, I guess, vector data structure which lives somewhere in memory. It has like a reference count, as do all, not all values, but all objects in. You know what? Let's maybe remove the reference count. Let's just go with a conceptual model. So we have this value that represents a linked list. And really it just contains a pointer to some buffer somewhere, or some array or whatever. And that has a reference count and then the individual items. So item, and so on. And the vector just has this one and maybe also a len. Like this is the array, I guess, and then a length. And when you push something to a vector, what you would do is you check if the length equals the length of this buffer. Oh, yeah. I think this buffer also needs to know its own length. Yeah, you can check if these are equal, and if they are, then you just need to allocate a new buffer, copy all the data over, and then point to that new buffer. But if only this buffer is built in, I think that's enough of a primitive to enable you to write efficient data structures. Although a question is, what if you have multiple vectors or multiple lists pointing to the same buffer? Then the entire buffer would have to be copied over to some new location. Which makes sense, I guess. Yeah. There was something I don't like about this approach. Let's look how strings are represented. Let's maybe clarify the data type that the language provides to us. I think the language should provide some sort of buffer, or let's say array of some t, and then also functions that operate on an array, like create array that maybe takes a size, aka an int, and then an item that is used to fill every slot of the array, which we need for this to be memory safe, because we also want get and set. Getting something from an array of t with an index, and that returns you a t, and this one returns you an array of t. And similarly, set takes an array and an index and a t, and it returns you another array. These are pure functions that we can offer on arrays. The way that arrays could be implemented in memory is by having a reference count, a length, and then the individual items. I think that is a sane design that allows us to create an array, get items, and the set function, because that is implemented by the compiler, it can actually check the reference count. If the reference count is 1, then it knows that this is the only reference to the array. So it can just modify the array in place and return that same array instead of dropping the original reference and creating a new array. And for a lot of code, I think the reference count will be 1. Because a lot of times when you push something to a list and that returns a new list, you actually just overwrite the existing list, or you create a new variable. You only use the new returned list and never touch the original anymore. So in that case, the ownership of the list would be kind of moved into the push function, and the ownership of the underlying array would be moved into the set function. So the reference count oftentimes will probably be 1. Which means we can efficiently modify such arrays, even though the language itself is completely pure, completely immutable. It's basically opportunistic mutation, how that is sometimes called in the literature. Okay. There was one aspect I don't like about this, and that is, I think I want a way to represent sub-slices, sub-parts of the array. Because if you imagine strings, a string might be something like this. Just if a string is just a pointer to the actual bytes, and a length, that that is actually not enough to build efficient substrings. So if you have some really huge giant string, taking a substring of that, we can't just point somewhere in this object, somewhere in this array, because arrays are garbage collected as all other data structures. So we actually need to store a reference to the beginning of the array. Well, store the array, basically. And then a start position and a length. Yeah. So basically string would be defined as string is a struct with bytes, which is an array of t and a start position, an int, and a length, which is another int. Yeah, sorry for my handwriting. And that means once we have this kind of array definition, we can this kind of string definition, we can efficiently get substrings of that, but just changing the start and the length. Yeah. Although what I don't like about that, what I really don't like about that, is how to we basically can't detect if we have exclusive ownership over that array or not. So for a list, for example, I think for lists we also want to allow you to efficiently get sub-lists from that, which means the definition would have to be something like this. And then this is also sufficient to grow the array on demand. So we could have a list, this is like an array list in Java. First create an array with a length 8 and maybe store one item in there. And then as you push new items to the list, it will actually check if this length is equal to the array length. And if it is, then it will just allocate a new array, copy all the items over. But if it's not, then it can just use the set function on the array to set a new item. Like, for example, let's say this is our list of ints. And this is an array list. So this will actually, well, let's say it has a capacity for 4 items, like that. Yeah, that's 4. When you say add something to this list, your list dot push a 2, for example, and currently there's a 1 in the list, and this is just some garbage. And you assign that to list. And the original list variable is only used here. There is no reference to the original list, so the reference count of this array is 1. What we would do in that case, we could, the list could check, is this length, currently 1, is that equal to this length, currently 4? No, it's not. So we just call this array.set function with the index 2 to store the 2 in here. And because the reference count is 1, that will actually modify the memory directly instead of allocating a new list for that. That's the idea. And then when you push something else, like a 3 for example, we'll just fill this memory up until the memory is full. And then we know that, we'll just copy the, when you push something, then we see that these lengths are the same, so that the capacity of the buffer is exactly the current kind of semantic length of the list. So we'll allocate a new array, copy all the data over, and use that, and return that. And the original array will automatically get freed because the reference count reaches 0 at the end of the function. However, that doesn't work well with sublists or subslices. Like, let's say you have some giant, giant list. Like, you read some file. It's super big. It's a list of bytes. And then you get a sublist of the first 10 bytes only. And then you set something in there. You just want to push to that sublist another byte to get like 11 bytes. What you'd actually end up doing is, well, you can't really, you basically have two lists now. You have one list that contains a pointer to that same object, so the reference count is 2, and start is 0 and length is 10. But when you push a byte, like there is no way to check if the reference count is actually 2 or 1 within Plum code, because Plum code can't, data structures are immutable. So within the Plum code, we would have to use array.set, because we can't distinguish between a list currently being built up from the ground up, or we are a sublist of some giant list, and now we want to push something to that. So we'd actually copy the entire big file, the entire big list, again, just to then overwrite the 11th item and represent the sublist of that array slice. And that I don't like. That I really don't like. Yeah. That was difficult. Also, another aspect I don't like about this is when strings and lists and so on, they contain an array inside, and basically information about where to start on that array and what the length is. Technically, when you get a substring from something, okay, so you have some big file and it contains some data, but also some other secret data, and you get a substring of the first data. Well, technically, the string data structure still contains a reference to the entire array. If you have a function that accepts a string, you could just ignore the string start and length and just access any item in the original array. Kind of leaks more information. This kind of design makes you leak information to more places than you need to. Yeah. What about adding just another level of indirection? What if what if the language provided an efficient way to get like a sub slice, you know? An efficient way to say, please, I want to get a slice from this array with, I don't know, a range of integers. And that returns you a new array that shares the underlying memory. Yeah, but then when you set something on that slice, and the reference count is not, the reference count of the underlying actual buffer thing is not 1, then we would only copy the like the necessary parts of that. I don't know if that makes sense. Let's maybe draw that out. Yeah. Basically, I'm proposing that this right here is not, like this right here is an array. And this is some internal type buffer or something that you can never reference from plain code directly. You always go through an array that maintains a start index and a length. So then the language runtime itself can give you efficient, ways of accessing a subslice. And once you've done that, you can never kind of escape from that. You can never grow, like look besides, like anywhere outside of this range that the array represents. Yeah, I think I like that. Yeah, let's maybe prototype some code. So let me switch over here. And yeah, let's look at some code, maybe in the playground. So what I'm proposing is to have some sort of array data structure. Define the type array t that comes from, that's like a built-in type. Then there are also functions on that type. There is create array that just takes a size and a fill item of some value t, and it gives you an array with that size filled with that item. Then there would be kind of like a get function that takes an array and an integer and returns you a t, a set function that takes an array and an integer and a t, and it returns you a new array. I'll try to write them below each other. I think that's actually fine. Yeah, we'd also need some, I don't even know, some slice function that takes an array and a range of ints and it returns you a new array. That's the idea of this. Yeah. I actually like that, having a one function per line. It is pretty, like a table of contents in a book, Also for the exports. Pretty cool. Alright, so yeah, let's maybe rename this right here to linked list actually, because I think the one default list data structure that I want, that should just be like an efficient array list, not a linked list. Linked lists are notoriously inefficient. Let's maybe replace all references of this with, well, maybe not. These with linked list. Right, these don't even exist anymore. Exports are kind of fucked up right now. Okay, we have linked lists. Yeah, let's rename that to linked list as well. Let's just import that correctly. Cool. Then, cool. Yeah, then I want to create an actual list, and that's going to be more of an array list, I guess. So let's implement that a list of t is really going to be an array of t and length, I guess, which is an int. Yeah, that is pretty cool. And yeah, you can create a list of let's maybe offer the same functions as a linked list, but kind of more, array list like. Okay, so we'll be able to create a list of some t, and that's not going to create a new list node here. No, it's just going to create, I don't know, a list, an array. Yeah, that's going to be create array of size 1, like let's say size 8 of the filled item of A, but the length of that is actually 1. So even though we have space for 8 items, we only use 1 of these. Yeah, length doesn't need to be a function because that's already a field there. Is empty is, yeah, perfect. Get maybe. That will be way more efficient because we don't need to traverse the list. We can just do, does 0 to list.len contain the index? If it does, then we do list.array.get get that index. Otherwise, we return none. Oh yeah, this needs to be summed. Yeah, we just immediately get that from the array. Alright, yeah, that seems reasonable as well. Then iterating on a list. I think that just keeps a cursor. Maybe. No, we'll check is the list empty. If it is, then we'll just return empty. If it's not, then we return as the item. Well, getting the first item from the list. And we can just do get maybe at position 0 if there is none. Yeah. If that is some item, then we just have that in there. And the rest is going to be, hang on, the list dot slice from 1 to list len. Iterating over that. Yeah, okay. Oh, and the cool thing is we're going to have a push function that is actually efficient, appending something to the end of the list. So this will take an item and it will just return a new list. And what that does is it checks if that still fits in the list. So list.array.len, if that is equal to the list.len, then to do if there is still space in the list, then we just set the array item. So we do array dot set at the index list.len, set that to the item. That returns us a new array. So we create a sufficiently sized array. And in here that's just the array, and here that is I guess let's create a new array of the size, well, the current array size, times 2, filled with something. The item, maybe. Sure. And then copy all the items over. So here we can just take the sufficiently sized array, set the item at the list length to the item, giving us the new array, and then we return a struct with that as the array, and the length being the list length plus 1. Yeah, copying the items over though. Not sure about that. So we'll need some sort of copy function that takes a destination array, I guess. And a source array. And then maybe a range where to copy that to. And that returns a new array. Ooh, yeah. Yeah, like that. And we can just check if the range is empty. Then we just return the original array, everything's fine. Oh, first of all, let's check that the source array length is equal to the range length. Yeah. Yeah, there's an assert function. Yes. Okay, if the range is not empty, then this will call itself recursively. So that will be the copy to with destination being destination dot set at the range start position. Set that to, well, source dot get 0. The new source will be source dot slice from 1 to source.len, and the new range will be range.start plus 1 to range.end. Cool. Yeah, this needs to import some stuff, in particular ranges. And integers, and the equals function, and plus, yeah, and also the to function for ranges. All right, yeah, and also assert. And that means we also need bool. All right, here we go. Cool. Yeah, and I think then we have an array list that just grows items. Yeah. And this right here, creating an array list with 2 items, would just be creating a list with 1 item and then being like push the second item to this. And with 3 items, that would just be creating a list and then pushing the third item. seems reasonable, I think. And yeah, all of the imports, need to fix those. So yeah, no built-ins, but we import stuff from array. Yeah, the array key, create array. Yeah. And here we can copy not sure about the name. Copies the source items into this array, the destination array at the range. Yeah. And this just copies the original array, so array to 0 to greater than, oh hang on, sorry, that would have been too readable. Nice. Maybe if the array length is 0, we should handle that. So we'll take the maximum of array length times 2 and 8, let's say. And then this creates an array with a new size filled with the item, and we copy the original array to the first half of that, or the first part of that. Yeah, okay. You can push something, you can get something, you can also efficiently get a sublist. Like, let's say slice. On a list of t with a range by just getting the lists, by returning something with an array. Yeah, I think this just shrinks the list to the array size. Yeah, let's have a shrink function that takes the list and just returns that same list, but it just says the array is just list.array.slice from 0 to list.n. Yeah. Yeah, getting a subslice from something would just be list array sliced from, well, from that range actually. And the length would be the range length. You know what, I think this can be simplified to just being the, maybe put that afterwards. Yeah, to just being list dot slice 0 to list len. Nice. All right. I like that. New list type. That is really just an array list. Cool. Then I actually need to implement arrays for this to work. So let's see, an array. Let's just compile the code and see where this breaks. Yeah, the built-in array type doesn't exist. That makes sense. Actually, let's use the list in here, just to make sure that works. List 1, 2, 3, and yeah. Maybe dot len, sure. We do need to export stuff. Okay, we do. I know that is the linked list. I want to export stuff from the list. What? Yeah, and you can push items into the list. You can efficiently get subslices from that. Len is not a function. So slice t range int. You can shrink list. Nice. All right. Pretty cool. Yeah, let's implement these built-in types, I guess. Try to use but that type doesn't exist. Oh well. That seems correct. Or that, or that. Nope, that not. Now we are compiling a toast type. Okay, so there's this built-in types thing, which is probably in built-ins. Maybe built-in types. yeah, so type array of something primitive, right? Yeah, and type array doesn't exist because that is defined in here, I think. And that should be defined in here. Yeah. And that's actually a function that accepts a type, which is a font type, and it returns, oh, look at that. So primitive types should have arguments. Maybe, yeah, let's maybe resolve this to do. Let's have type variables and then primitives, which I could add a type for that. Okay, maybe that makes sense. Yeah, primitive type, you know, int string type array or rather than doing that, I could just inline them here. Oh wow. Yeah, I like that. Yeah, primitive is no longer a thing. Instead, this would just be content.int string type never array of that type put on the heap. Cool. Yeah. Nice. Yeah, I know some of this has to be adjusted, but that is fine, I think. Yeah. So if these are two type variables, then they have to be the same. I get that. If this is an int, another option would be to have to have something like primitive that actually is just some struct with a name maybe and the arguments. I think that's actually totally fair. And then these can all be handled uniformly in the type checking. Yeah, sure. So this is a primitive type name is a string, the arguments is an empty slice of types. Very similar for ints, very similar for types. Yeah, then array would just be primitive array type. The argument being a list or a slice containing the type that we were passed. Alright. Yeah, and then in here we have type variables, sure, and then primitive types. And here we need to check if the primitive types are the same. And well, the names, yeah, the name has to be the same, and the args have to be the same. Yeah, hashing that, well, we now have var as well. Super elegant, but I don't know. And then writing down a variable. Well, this would just write the name down. It makes sense for the primitive. Yeah, that writes down the name, and then for every argument, the argument. Alright. Yeah, collecting other type variables. Oh, look at that. This is way more elegant because we just do out.name, and for primitives, well, yeah, we do args.collect type variables. Oh yeah. Nice. Then in here, we don't need this switch anymore. Yeah, because we now do model these. Is type variable? Well, then we do this. If it's a primitive type, then well, primitive, complete primitive, and then we check that the names are the same, and for both in concrete primitive.args zipped with generic primitive.args. We just do match against. Oh, hang on. Is there match against with slices? Yeah, there is. Okay, that's pretty cool. So we can just do concrete primitive.args match against generic primitive.args. Nice. Mm-hmm. Oops, sorry about that. Nice. Alright, what do we have here? Match against, oh yeah, this needs extra arguments like the constraints and what we are currently matching. True. You don't handle plum type.var. Very true. Yeah, this is a type variable with some name. This is actually where we do that. If that's not the case, then we need to nice. Yeah, and in here we just build primitive type. Very nice. And then, I'm just going through this file and checking things. Hang on. Yeah, so var of some name that is just plum type var of that same name. Yeah, primitives, they get a bit more complicated here. Because in arrays, for example, you could have a recursive type that then references another type. So we need to go through the arguments and we'll extend these as well. So what do? We build up new arguments, which will be a list of plum types, and then for every argument in the primitive arguments, we just push that into this one, and then we return a plum type primitive of a primitive type with the same name but different arguments. Yeah, and that is the original struct, except the arg that we navigate into. This arg has been replaced. with a recursive type. Okay. Sure. Yeah. That is like dense code. Nah, yeah. We're just building something that's similar to structs and enums and so on. So for every field, for every arg in the primitive arguments, kind of like that. Yeah, replace recursive level. All right. So is equivalent. If they are the same. They need to have the same name. Okay, for primitives. this is a primitive, then B also needs to be a primitive. And then if they have different lengths of arguments, that's bad. Also, if they both have the different names, that's also bad. Yeah, and then if the arguments have the same length, then they also have to be equivalent. And if all of that is true, then we'll just return true. Union logic. So let's say we have two type variables. Oh yeah, they have to be the same type variable. Yeah, okay. Makes sense. Okay, for primitives, they also need to have the same name. So B has to be a primitive, and these primitives, they need to have the same name. And then, similar to what we do with lambdas, the arguments, they don't have to be, yeah, let's say they have to be exactly the same. Sure, why not? Loosen this a bit, yeah. I don't know, hang on, like if we have an array of only true values and an array of only false values, they should be joinable to an array of bools. Oh yeah, but then we'd have to implement casting logic for that. So loosen constraints, and I implement this requires implementing casting arrays. Yeah. Currently these just have to be exactly the same. Sure. Alright. Yeah. Slowly we're getting there. What else fails? And crystal add types. We create that with a type variable. Yeah, and now I'm just following the arrows, I guess. And this is supposed to be a type variable. In here, yeah, if that is a variable, toast type. Yeah. Okay. That's an outdated error. Let's see. Oh yeah, we create an egg operation with a time type.var. Yeah, that's just that. yogurt. Yeah, this should only be called after types have been specialized. So this should be unreachable. Yeah, that's true. What do yogurt types look like? We have primitives which just contain string. Well, that is not sufficient. So, yeah. I think in this, I think here I actually want to split that up into the different types, like int, string, array of some type. Let me double check what the built-in types were. Int, string, and type. Int, string, type, and array. I mean, these are not parameterized, so yes, that should just work out like this. For arrays though, yeah, that has to be the same. Well, let's improve the hashing function a bit. Cool. need to switch on the type. So if name is int, then we just return, give it type dot int. Because we type check that these built-in types are called or referenced with the correct amount of arguments, this should always succeed. There should always be a singular argument here. Where's that? Types. Up here. Oh, look at that. Now we just do, if this is an int, then it's going to be pesto type int. Boom. If this is a string, then it's going to be, well, I don't know yet. I guess just pesto. If it's a type, then it's this right here. Boom. It's an array. Then to do and my plan is just to get there. To pesto on the type. Oh yeah, then it's not needed here. Is recursive. Int is not recursive, string is not recursive, type is not recursive. Array may be recursive. I mean, then we don't need that if, but it is consistent. Sure. Let's keep that. Dupe drop 3. Yeah, in here, compiling a dupe fun for ints doesn't do anything. For strings doesn't do anything. For types doesn't do anything. For arrays, it's a to-do. Then dropping things, same thing. For ints, don't need to do anything. For strings, well, it's gonna be a to-do. For types, nothing. For array, gonna be a to-do. In types, down here, assert no closure. Oh yeah, basically uncompile that type plane, which is kind of crazy. Yeah, int will just be, yeah, exactly that plain type, a primitive of a primitive type with the name int, the args being an m. I think there's a type int, yeah. Very nice. Oh wow, it compiles. Yeah. Quite cool. Okay, so in core type import built-in stuff type, but that doesn't exist. That is strange though. First of all, let me get rid of some of the errors here. But in, like, what is it, built-in type? Yeah, the type should be in here, in built-in types. Yeah, here's the type. Oh, I see. And that is the name. Never mind. I mean, yeah, these are built-in types, so primitive .name. Dang. Yeah, maybe. What the? Interesting. Oh wait, that is not even, that's an error in the compiler, I think. Maybe primitive type. Oh no. Where's that? Oh, this is maybe primitive type. Let me unwrap that. Weird that it just throws an error there instead of you know, telling me that is wrong, but meh. I mean, all these built-in types. We have type int, string, type. Oh, never is not a built-in type for some reason. I guess that makes sense. But also, this is, where is that used? Is that only used down there? Yeah, these are like different built-in types. And these and these. Okay, yeah, we have this. Then we have this. Okay, sure. Compile all types. That does put the built-in types there. As like dollar something. But this is also not correct, so I think I'll actually change that. Hang on, this is compiling a toast type with some environment. Okay, what is this doing? It looks almost the same. Type using some defs. Not sure. Honestly, I'm not sure. Yeah, but I think I'll just remove that. Yeah. I'll just specialize that. So if the variable string is int, then just return okay with a, what is it, type int. Yeah, and same here for array. And if caller name is array, dollar array, I think. Yeah, I think of the toast. They can't get dollars in front of that for some reason. It's just meh. What was it before? With dollar prefix, yeah. So that you can't define a type dollar int in your code. And yeah. Okay. Yeah, in this case, we will return type array, type array of single argument. And down here, yeah, initially we'll have to create these types. Yeah, this is where we put the dollar into these. That is $int. And then string is just $string. I mean, hang on. I don't have to do this. I could just check that above. We'll add it to the okay, we have int, we have string, we have type. We have array, and that is not interesting because here the parameter is not an empty slice. No, this is actually some heap. This looks exactly like the code above. I feel like one of these is not used. I'm assuming it's this one. Try to use $array, but that type doesn't exist. Okay. Yeah, $array is not a type variable. It is a type. It should be a type call. We just say var, and this is a call. Yeah, var call, and this is something different. Okay. Array is a variable. Interesting. Maybe just print the type. I mean, maybe that's a valid error, you know. Although, yeah, I should associate a type with that. Compiling built-ins.array of t. Yeah, that makes sense. So we're compiling the t. And we're compiling $array. Oh, hang on. In here. Oh yeah, this is defined as a type variable, but should be defined as a call. This one. Yeah. With name being $array and args being a list of a toast type variable t. Oh, is it like, yeah, it's variable spelled out. Nice. Okay, apparently this down here is used for something. That's a pity. Why though? Like, compiling the toast type. And after we've compiled all the types, I went to plum type defs. Okay, I guess. I don't like that at all. I mean, for now I'm gonna go with that, but that is kind of nasty. Yeah, and same for the called definitions. Here we will just have something like that. No, I don't like that. Ooh, okay, we actually get useful errors. So in the list plum file, we don't import iterators. Look at that, substitution for T missing. And specialize. Does seem kind of random. I mean, let's maybe convert that toast to an egg. Okay, empty substitutions. I don't get it. Let's maybe print the function that we're compiling. Converting something to an egg, compiling a function. Yeah, at that point we want to print the function. yeah, compiling fun enumerate. Yeah, sure. Let's print the individual expressions. And I think I'll get some tea. Fitting for the substitution for tea is missing, so I'm going to get some tea. Here I am with tea. Very nice. So why doesn't that work? I feel like we should get more information, shouldn't we? Or at least, let's see. So we have some sort of call to the plus function, I guess. Let's maybe look at the source code of the enumerate function to kind of get a feeling for what's going on. That would be an iterator enumerate here. Probably this one, yeah. And we get a start index plus 1. Yeah, so we have this call of the plus function of the start index and 1. So what we do is we first compile the start index, and then we compile the 1. Fair enough, yeah. And then we specialize some ordering stuff. Oh, I think because now I'm still converting that to egg. Where's ordering stuff going on here? That doesn't make any sense. I don't get it. What to do about this? Oh, what's even weirder, there is no t in this enumerate function. It's an iterator of a. That is what? Let's look at the playground, I guess, maybe. Oh yeah, here we use t, but let's maybe trim this down into something that is more easy to analyze, you know. Yeah, so let's remove all unnecessary stuff, like this. Still the same error. Okay, let's copy the standard library and just paste that in there. Core copy, sure. And then our playground imports core copy. Oh, yeah, okay. Apparently spaces in the name are not great. Let's put a hyphen in there. And core copy list. We are referring to maybe, yeah, that is actually correct. Why is that a different error? Doesn't make any sense. Yeah, unwrapping a maybe. Oh, string. I see. So we need strings. I see, yeah. Okay. Now I'll try to trim that down. First of all, this list stuff that makes sense to have in the real core library as well. Yeah, but apart from that, let's just try to remove stuff. Let's remove most of the iterative functions. Apart from next. See if that's the same error is still there. No. Different. Okay. Let's re-add them. Let's remove only some of these. Same error. Okay. I mean, I guess all of the ones that don't contain T can't be the bad one. I'm gonna leave enumerate just because it was kind of weird. Oh, this doesn't even compile, does it? Nope. Doesn't help that it's so unpredictable. List.array.len. There is no function named len in scope. That is true, yeah. Hang on an array, yeah. So I actually want to, first of all, not do that, maybe do that, I don't know. Oh yeah, that should be a built-in length function that takes an array. I think let's call these length. You can spare the extra letters. Yeah, okay, let's call that n and then fix that later on. Always a good start. In the list, I want to import that. Oh, hang on, what? List.array? Oh. Oh no, that is, yeah. Array should be an array of t. Okay, now we're getting somewhere. Let's remove some more iterator stuff. See if that still happens. Nice. Okay, now I can basically trim this down. I can say, yeah, let's remove maybe iteration from there. Let's first of all copy the list because there were some fixes there that are, I mean, you know what, those fixes are easy to do. So let's just simplify stuff. Okay, substitution for t missing. I think we don't need any types. Let's remove that entire thing. We don't need any tests. We don't need results. And the only thing we need here is list int and len on list. Yeah. You know what, let's maybe inline the list definition into the playground. And let's see, list depends on a lot of stuff, on bool, int, iterator, not really. Maybe on string, on range. Yeah. But not really on string, not really on that. So let's also copy the bool. And the what else was there? The int. And maybe and range. then, oh hang on, let's also look at these. So bool depends on string, okay, sure. Which imports the built-in strings, that's the main crazy stuff it does. Let's do that here as well. Okay, sure. Yeah, that's bool. Then we also had maybe. You know, let's just take this, remove this, and see where it fails. Yeah, array doesn't exist. Fair enough. Let's take all that array stuff in here. Just dump that in there. Beautiful. Okay, and then int. Hang on, but I already copied int, I think. But not the imports up here. Not these ones. And then ordering. Okay, I have a self-contained file that fails. So let's remove this and just trim down this file. So I know that I don't need the, I mean it's like, what, 340 lines. Better than the entire core library. I know that I don't need int formatting. And iteration stuff. And, well, this one, square root or log2, or what have you. Yeah, formatting bools. Some of these more obscure things probably don't need them. Substitution for T missing. Okay, still that same error. What about rather than creating a list, I just call create array with 1, 2, and 3. And how about I just remove the entire list stuff? Alright. Same with ranges, because why not? That is true. Yeah, let's keep the range type, I guess. Yes, and maybe stuff. Nice. Oh, I can see where this is coming from, probably from here, right? Yeah, that is true. Create array doesn't exist. Let's say filled array, maybe. Of length 3, filled with 42. filled array, I guess. Oh, yeah, that is indeed true. Yeah, let's fix that first. Let's create a built-in function. Yeah, int operations, string operations, lambda operations, array operations. Yeah, filled array. Yeah, and all the other, like these ones. Then int and a t. Array get, array set, array slice, and array len. Cool, yeah. Then in the built-ins, we'll actually have the ints and then also these. Compare ints, that's the last one. Then we have concat strings, and then we have several array functions. So we have filled array, which creates a filled array. So the argument would be type int, and then a type t, which is actually the plum type var of the string t. Yeah, that returns a type array of that t. Kind of like that. Beautiful. Then there is array get. Which takes, well, an array and it returns t. There is array set, which takes an array of t and then an int and then a t, and it returns another array of t. I think I want to create a type t, so I can more easily use that. Let's maybe create here a type var t, let's say, and that will just be a type.var t. Yeah, so then all of these can be simplified to just type var t. Nice. Making these even shorter. Alright. Yeah, array set, and then what else? Array slice and array len. Slice accepts that an array of t and then a range of int, and it returns an array of t. Type range, is that defined? Maybe not. Have to fix that. Oh yeah, this is type linked list. And yeah, type range of some item, I guess. So that will be some type dot struct with a map that maps start to the item and end to the item. All right. And array len, last but not least, just takes a single array and it returns an int. Nice. Oh, too many built-ins. Well. Let's add some more functions to the RGA standard library. Oh, where's that list? Here. On NLP Q. S. Well, no, hang on. Let's do this. Q. R. S. T. IJKLMNOPQRSTU. I mean, yeah, come on, let's do the entire alphabet, why not? V. W. X. Y. Oh. And Z. Look at that, it totally fills 2 lines. Exactly. That's pretty cool. Hopefully there's enough functions. Yeah. This, on the one hand, this is super cursed, but it's also a bit fun. Main. Funny. Yeah. Type list, true, that has been converted into type linked list. In here. Yeah, I guess this is return my linked list. Not entirely sure about that. Okay. I mean, this is also not up to date. yeah, type info, I'll need to think about that and update that. What I'm gonna have to do here. Well, more specifically here. Then your filled array. I don't handle that. That is indeed true. In here. Oh yeah. Okay, when specializing some built-in, yeah, we're handling ints and strings and filled array. Well, that would just be yogurt built-in dot filled array. Yeah. The same for array. Array get set len and slice. And on the yogurt, that we have to add those as built-ins. Means on instructions, we also need to add those. Yeah. Filled array, array get, array set, array slice, and array len. Nice. Don't handle instruction filled array. That is true. Yeah. All right. Okay, yeah, built-in stuff len doesn't exist. That is true because that is called ArrayList. So in the playground, let's say we import built-ins ArrayList. Yeah, and this not really. Yeah. And here what we're really doing is ArrayList. Yes. And same here. so this does need some range functions. Oh, there was no len. Well, minus. Yeah. And now minus doesn't exist. Well, what now? Equals equals. Yeah, let's just remove that. Get. Yeah, no, that is array get. And that is array set. Now I'm adding back all the functions I removed before. Oh no. Slice. No, that is array slice. Okay, that is a different, completely different error than before, which is interesting, I would say. Let me make like a minimal one thing where I just copy all of that too, so that isn't lost. And then, yeah, I mean, let's import the standard library function. So I want filled array. taking an int and a t, and what length of an array of t, and also array. And int. Okay. Yeah, that is .call. 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 Yeah. Why? That kind of sucks. I guess let's just fix that first. And then, so this will be filled array, like fill array, maybe? Filled array, yeah. With array get, and array set, and array slice, and array len. Okay, and then we'll have, well, it will export filled array. We'll have get on an array with an index. That will just be array get of that index. Similarly, we'll have set with also takes an item, returns a new array, and that will be array set of that item. Yeah, we'll have array slice. A slice that takes an array and a range of ints, and it's just going to return different array by doing array dot array slice with that range, and finally len of an array. All right. Well, that didn't really help me. Hang on. Okay. We're just having a toast type in here, and we want to convert that to a plum type. So we see which type we called. And the parameters of that called definition, we substitute our arguments, which are concrete plum types. Makes sense. And then we specialize that call, that type with those substitutions. Okay, makes sense. So then, these three places. We do that for the return type of a local function. Computing return type. Oh, so compiling. We do this right here. Oh, also the return type. Oh, I see. So this is the return type of the local function. And this right here is the return type of the built-in, and here's the signature. And then this here is specializing a cast for a call. Let's see. Okay, so we are compiling the return type of this built-in. Okay, so the plus function is there. No, not that. What? I mean, what? Specializing an array. Where is that even happening? Now, we're printing all the specializing stuff here. Let's even disable the rest of the compilation pipeline. Let's say we only compute the egg, and then that's it. Yeah, still same thing. And it doesn't say specializing call before this. Nope. so this is like run, which is not even used, right? Yeah. Then there is this commented out. Specializing cast for call. How does what? Why is that not printing anything? Okay, so we're compiling the return type of this plus function. And then to do that, we're specializing stuff. What the hell? This makes sense. This makes sense. This makes sense. Makes sense. Makes sense. Then at some point was compiling the return type of plus. Suddenly it doesn't specialize in, but it specializes this. What? And then it returns string. And then array of t. How is that even return type of built-in? Let's see. And let's maybe print the unspecialized version. Yeah, that arguably returns an array of t, which is just wild. Why? This calls built-in not signature. Oh no. I see. This is just built-in. Signature has nothing to do with that. Oh, we're just using that to compute the built-in signature so that we can then compare them. Oh no. I guess, yeah. Not great. Yeah, okay. That is more what I expected, yeah. Okay, compiling the return type of built-in concat strings, yeah. Compiling the return type of built-in filled array, yeah, there are no substitutions. That is correct. Hang on, what do we need that for? We've imported something, and that is a new signature. case here. Yeah, I would say let's factor this out, you know, into some sort of compile call or something. Okay, here we figure out the function name. Okay, I'm fine with that. And if that's a top level function, all of this is just for resolving functions. And so on. Not even that, this is just for finding the function. Yeah. Also, like, how is that not in lookup, you know? There's match against. There is collect all funds. Sure. There's a signature, but there is no lookup in here. So I think I'll put this into the file first. This is the lookup. Yeah. Yeah, the visible functions, that makes sense. We need those. I think that's just a list or size of functions. Yeah. Cool. And we need the map of all funds. That is, what is that? This right here. Oh, there's a set of string. Name is just going to be a string, and we have the source as a separate parameter. Yeah. one is the result. Sure. And then we have the full matches. And also takes the arg values. Sure. A slice of fun args. Oh, that is actually pretty elegant. Let's do that up here as well. Just return an error of stuff. And then basically do this in here. Yeah, then return an error of that and the source. Just like that. Yeah, that is clean. Also here, just de-indent that. Nice. Okay. I mean, that is quite a chunky function here. Types doesn't really exist yet. I am wondering though. I think I'll actually turn this into args. Make fun args something else. So, oh, fun arg already has a type. Well, so how are the archetypes created here? Like this. And where are they used in here? Only in here, I think. Oh yeah. Yeah, let's just put args in there, I think. Alright, yeah. here we would just look for a matching function. That is this right here is the lookup. Using the funds and the visible funds. And the name and the args and the source. Okay. I mean, how hard is it to find the return type of a function? That can't be so difficult, right? Looking up the function, we figure out the return type, which is surprisingly difficult. Yeah, if it's a local function, sure we can do that. If it's an imported function, check that it's not a built-in function. Because if it is a built-in function, for example the filter array function, then what do? We basically the signature, we import some signature. Okay. So we are importing filled array of int and t in our case. Yeah, and then we call this built-in info. I don't know. Yeah, anyways, we build a signature that consists of we turn type of that because array t. That's kind of weird. Oh yeah, in compile fun. Funds is just context.funds, I think. Yeah. Then in lookup, this is just args. Same here. Okay, let's get some more t going or flowing. Yeah, so a fun arg, we can't print that. Fair enough. Why do we try to print that in the lookup? Yeah, in here. Oh yeah, we print the arguments. I think we want to do that. Yeah, that's about printing these. All right, here we go. The last expression doesn't match that. True. Also true. This can fail. So done that. Now there should be, hang on, I added some logging above here and like this one, call matching something. Where's that? Call matching, where do we call this compile function? Oh, hang on, where are the substitutions? Why are we doing this? I mean, we're compiling the main function, right? Why are we are doing that while we are checking whether the built-in matches. I see. That kind of doesn't make sense. Just for importing. I mean, yeah, here we have the built-in with substitutions. But what? Hang on. For the local functions, we're doing something completely different. I'm wondering, where does it do this? Call matching something. Can't see that. Oh, up here. Yeah, but let me maybe highlight that. That just doesn't make any sense. No. No. You know what? Let's... I don't know what to do. I would debug this, but Martinez doesn't have debugging. I can only print debug, so... yeah, we're checking all the built-ins whether they match. And that alone is kind of wild. You know, compiling all the built-in signatures and specializing them. Using these substitutions. Should we maybe just not check for equality, but check if the signature starts with, you know, built-in module dot built-in. I think that's actually sane. Then we don't need this. Oh, I see. Oh, different error, I guess. Damn. Okay. Don't exactly know what to do about that. Let's see. Does this make sense? Double check that first. So we're checking if this is a built-in by just checking if the signature starts with built-in module.built-in. And if that's the case, then we get information about the actual parameters and return types. Do we even use that? No, we don't. About the return type, that is just that specialized. Okay. Yeah, and only if that matches, then we substitute that. We specialize that with the substitutions. That seems fair, yeah. Okay, so now we're dealing with this function, something doesn't exist. Oh, and there's a pain wrapping those in parentheses. Let's fix that first of all. Yeah, so for primitives, if arg, if primitive.args is not empty, only then do we print an opening parenthesis. And same for the closing line, just like that. Oh, that actually fixed stuff, maybe, I don't know. Okay, there is no matching function named slice for the argument t and array. Yeah, list.array should not be of the type t, but of array of t. Those were kind of backport some of the fixes that I had in the copy. Okay, and now we have the same error, I think, of a function not existing. Yeah, workspace.core filled array of int and t does not exist. Workspace core.filled array of int and t. workspace core array dot filled array. Oh, hang on, that might actually be the case. So we just don't import that. Yeah. This is called filled array. Nice. Okay, we're slowly getting there. Let's double check this as well. We have get, we have set, we have slice, and we have len of an array. Yeah, len of a range. But we need to import that here. Range.toInt doesn't exist. Really? Where is that used in list? Yeah. I guess that's correct. There is no function contains in scope. Okay. Range int and some number in list. And then .get. There is no function named get for the argument. Oh, just an array. Hang on. Oh, because this is in an enum. That is actually, that's nice. I mean, that's actually an error, you know, on the call side, not same here, by the way. Yeah, and then here we have len does not exist in the array module. Yeah, let's import that. Let's say we also want len of the range of ints. Yeah, that is empty on a range of ints. Oh man. 2 function range 2 int doesn't exist in core array. Oh yeah. Yeah, create array doesn't exist. True. That is filled array. Oh no, it's correct like this. Filled array with new size and item, and then we copy the array. That's range, yeah. Okay, so list also needs the len function on arrays. True. Star. There is no function named star in scope. Let's change that. Nice. There is no function named max in scope. Yeah, I think that's in Quadro as well. Maybe. Yeah. There is no function named copy in scope. Let's import that. Okay, now re-enabling the rest of the compilation pipeline. And let's see. The only thing I want is that the egg gets correctly created. Oh, dang. Yeah, we went far. Even into the yogurt. That's pretty nice. Yeah, let's remove some of the debug prints. Definitely. Like all the specializing stuff. And yeah, even these commented up ones. Okay, so there is still specializing in here. Yeah. Plus there was call matching. Now let's simplify this. pulling yeah. Okay, that's perfect. Yeah, and then let's print the egg, I guess. Oh, maybe the yogurt with only the used functions specialized. Yes. Ooh. Yeah. That is nice. Calling the array len for an array of ints. Here we're calling filled array with a 1 and a 2. Nice. Very cool. Very, very cool. I think that's it for today. That was honestly more work than I expected. Just getting primitive types to work with type parameters and all the substitutions and so on. And the code is still not beautiful, it's still like, that is still some of the nastiest code that exists in this project, I think. Like, especially this kind of lookup stuff. Well, this is kind of contained now, but there's this compile function with this one giant function that does everything. That is, ooh, I don't like that. Yeah. All right. Yeah, I guess. Yeah, that's it for this time. And next would be, I don't even know. I guess implementing arrays in the rest of the compiler pipeline, besides type checking, which was way harder than I thought, but choosing memory layouts in the pesto. Yeah. Like, how is an array actually represented in memory? Doing that kind of stuff. That's gonna be fun. Yeah. Alright, so next up, implementing arrays. For example, let's say we have an array of 2 elements with filled with 42, and we get the length of that. Yeah, it says to do implement array primitive type. So that's what we're going to do in the in the pesto, pudding to pesto. And that makes sense, I believe, because in the pudding, yeah, we still have these pudding instructions that contain instructions such as, create a filled array, get something from an array, stuff like that. So these are still primitives in the pudding. In the pesto, though, they are not. Here we are much lower level. We have operations like create something on the heap. Yeah, so I am wondering, does this work? What is this? Alright, and in the pesto, the types were this: int, pointer, struct, and enum. I think now we need to add another type here. Because remember, this is kind of like the C abstraction level, you know. I think now we need some sort of array. Let's maybe model this in arrays. I'll leave it like this. So we have an array in our code is actually a triple, I think, of the underlying buffer, the start, and the length. And that points to a buffer, which is like an internal buffer type. Points down here, where we have a reference count, which is implicit in this compiler stage. So this just contains the length and then the items. Yeah. Very nice. So here we basically want some sort of buffer type. We can build this. That's just a struct containing, you know, a pointer and then 2 integers. And that struct points to a buffer. Yeah, a buffer of some pesto type. Yeah, that does mean that we need to adjust these. So if this, didn't share my screen. Well, here we go. So in, what did I do? In the pudding, I didn't do anything, but in the pesto, arrays are, they're treated like this. An array in Plum is actually just this. It's just a struct that contains a pointer to the buffer and then a start position and a length position, so that you can efficiently get like snap slices from that array. And a buffer just contains the length and then the items in memory. There will also be a reference count before that, but that's implicit in the pesto. Yeah, so I added here a pesto type, which is a buffer. Yeah, so buffer would just contain, in one case, buffer AA. Well, if B is a buffer, then the elements have to be the same, else false. And then here we have the pesto. Okay, sure. But what are the operations? Like, we need some way to construct a buffer. And I think the way to do that would be by, well, how are instructions? Oh, I see. We still have instructions in here. Yeah, that makes sense. Okay. So we'll just have, you know, we do have a filled array instruction that returns you a struct with a buffer and stuff like that. So we don't need to worry about the implementation of that yet. All right. So I just need to go through this and add cases for the buffer type. Doesn't really have a representation though, so I guess just buffer and then the item type should be fine. And then something to pesto, putting to pesto. Let's go through this from top to bottom, I guess. Yeah, an array is actually just a pesto type dot struct. And it contains a buffer, that's a pesto type pointer. It contains a start position, that's an int. And it contains an int, that is also an int. And that's everything there is to arrays. That's, the layout is independent of the size. Pretty cool. All right. Contains pointer. Well, for a buffer immediately stores the items in there. So we need to check if the item contains a pointer. And that's it. Yeah, this has nothing to do with pesto types. That is the module. I think we don't need to do anything more here. We can just, I think we now have a valid pesto. Yeah. And only the next compiler stage, pesto to waffle. That is where we'll need to, you know, worry about that. You know, what is the memory layout of a buffer? It's not known. Ooh, well, that kind of sucks. Yeah. Yeah, that's difficult. Maybe buffer is not the right abstraction here. Maybe instead we want some sort of special pointer type. So this points to a single item, and then we'll have some sort of multi-pointer. And let's say buffer pointer. Or we just don't do anything about that. That would also work. Yeah, I mean, here we don't need the buffer type. Yeah, true. I mean, that is kind of weird. You know, having a buffer type in here, but never using that. We never construct that. So I think I'll just remove that. Sure. Yeah, I guess. Even simpler. Yeah, and then in the memory layouting, we don't need to handle anything extra. All of that immediately works. Print to pesto and types. The code is simpler than I thought. Yeah. That's cool. It's just that arrays are really just this, a struct. Yeah, and now in the waffle, this is where we need to think about that. Not in the memory layouting of ins and pointers and structs and enums. No, not in the struct layouter or anywhere here, I think. Just for these functions. Yeah. So creating a filled array. With an item. See, that is actually quite complicated, I think. Allocate a buffer. See how that looks for new, something like this. We want to allocate memory first of all. Allocate memory, and I mean, this is horrible. Mapping.get in the arguments. I mean, we could just say the arguments is a list of ID, and then for every argument we do args.push mapping.get that argument. Yeah. Then here we can just remove all the mapping.get calls. Well, yeah, these. Maybe not all of them. Yeah, not down here. No, just just remove those. So just do args.get 0 and args.get 1. Clean. And this as well. Just get 0, get 1. for a filled array, first of all we have a length, that is args.get0. That is an int. Then what we do is that's a runtime known int, yeah. Then we push a waffle mul to multiply that with the size of an individual item, which by the way is args.get1. So we multiply that int, that item. With a waffle int that represents the item size. Yeah. And then we'll need to add 16. And that is what we allocate. All right. Now, this is supposed to be the length. Yeah, we multiply the length times the item size. Add 16, aka 8 plus 8. 8 for the reference count, and 8 bytes for the length of this buffer. Yeah. Then we will store stuff in there. How do we do that for strings? Do we do something for strings? Oh, I see. Maybe not. Oh, this is horrible. This doesn't work. Oh, we'll get to that. So this takes the string and then gets the literal address of that string in this Martinez program and puts that into the bytecode. That doesn't work. But strings don't work currently in general, so yeah, I guess that's fine for now. And I'm thinking about removing strings in favor of arrays. You're building strings into the standard library, but not into the language itself. I mean string literals, I want to have them, sure. But the built-ins shouldn't be string concatenation and stuff like that. That should be implemented in the standard library. All right. Cool. So here we have filled arrays. We have allocated memory for the array. Then we will store something in there. Oh, we don't have any form of loops, I suppose. That's gonna be interesting. I'll just I guess I'll set the size at least. Yeah, that's gonna be like a store. Right, we don't have store in the waffle. Oh, hang on, we do have store. Okay, fair enough. That's good. Let's move these. Nice. So I want to store into that pointer, well, yeah, a reference kind of 1, sure. How does that work for this new thing? Oh yeah, we store 1 into there. That makes a lot of sense. The builder is mutable anyways. Why the... Yeah, the builder is mutable anyways. Well. Yeah. So... we allocate memory, we store 1 into there. That's the reference count. We store into pointer plus 8. Hang on. Let me maybe get that. Put that in there. Yeah. Yeah, so this is not going to be an aggregate. This is just the waffle int 1. Then we add 8 to that pointer. And then we store the length. Very nice. Yeah, now we want to fill that buffer with items, which... well, I don't know how to do that. I think the best way would be to add some sort of waffle store n. Store multiple, I don't know. And then we store to waffle pointer plus 16. And the length times a single item. Something like that. That means I'll need to add some waffle store multiple thing. And then finally in the end we'll just build an aggregate that contains the pointer and the start position, which will be 0, and finally the length. That is our array value, actually, that points somewhere into memory. Yeah, in the pesto, let me go back here. This command is really out of place. Yeah, all right. So we have a filled array. Sure. Mm-hmm. I mean, this is yeah. More like a node. That return type or the return byte of compare. The compare ints waffle expression matches the tag for ordering enum. Boom. And here's the enum. Amazing. Yeah, and these can move them a bit further to the front. Nice, tight. Then, what else? This looks fine, except I need to implement waffle store multiple. So in the waffle, I want to extend that with a new kind of expression. Yeah, there was waffle store, but I want waffle store multiple. Times is going to be a waffle expression, and the value to store as well. Yeah, similar to that, we'll have a waffle store multiple. Pointer should be pointer, times should be an int, and then we push a waffle expression, size 0, alignment 1, kind is waffle expression, store multiple of a waffle store multiple with the pointer with the length, sorry, the times thing, and the value. Yeah, waffle expression kind. Nice. Yeah, of course that can't be converted to bytecode. We'll get to that. But first, let's see. And here, yeah, sure, those should be waffle expressions, I guess. Yeah, true. In optimize waffle, we don't handle the multiple thing. So can we copy this expression? Store is false, well then store multiple is also false. Optimizing that. Let's see. Where's my nice little store? Here. Store multiple. It's gonna have a pointer that is optimized. It's gonna have a times and it's gonna have a value. Those are individually optimized. Yeah, that makes sense. Alright, then tree shaking is pure. Well, store multiple is definitely not pure. Collect referenced. Okay, yeah, and then tree shaking. We have a nesting. Let's look at that. Count references. Without, okay. So I think for the store, we'll just need to count the references of, well, the referenced expressions. Pretty cool. Then try nest local. For store, what we do, the pointer is going to be try nest local. Same for the times, same for the value. Afterwards, yeah, like they can't be moved beyond the store. Sorry, the store multiple. Alright. Yeah, try nest param is even stricter, where we have this store multiple, where we store the pointer, then it must have already been used, and then we just store the times like that. Alright. Neat. Okay, so the waffle should be done. What's going on here? Waffle optimize. Yeah. So waffle to ground, that is still a to-do. Alright. I mean, yeah, ArrayList, these other functions, true, didn't think of them. But Still need to do that. Very true. So we can create a filled array, which is essentially just a struct containing a pointer, a start offset, and then a length. Nice. So to get something from an array, really what we want to do is, well, let's get 0 is the array, let's get 1 is the index, first of all we need to check that the index is less than the length. Also that is larger or equal to 0. No. Yeah, so I guess I'll need some sort of waffle switch. What does waffle switch look like? Waffle switch has a byte and then the cases, which will be waffle bodies. So the byte is just the result of comparing something to 0, comparing the index to 0. And then the waffle bodies, well, not quite sure what the body is. I think I need 3 bodies here. The first one was for equal. If the length is equal to 0, then we just if the index that we want is equal to 0, we do nothing. But what does a waffle body contain? Let's see. Locals and returns. Does a waffle body have do we have a builder for that or something like that? Maybe not. In the waffle maybe? We have the waffle and the expressions, constructors, various different constructors, writing stuff, and that's it. Well, okay, I think that's fine though. So in here we'll need a waffle body with locals, I think that was. which was a slice of IDs, which is just an empty slice. Hang on, there is empty slice. Yeah. And a return waffle expression. Is the waffle nothing? Maybe not. Yeah, I guess padding 0 is fine. Yeah, and we'll need 3 bodies. The first one is for equal, then greater, and then less. So if it's less than 0, the index, then, well, then things are bad. Then we actually just want to crash. That requires a message pointer and a message length. Yeah, here's message pointer and message length. All right. Then, next step would be this down here, showing that the index is less than the length. So we'll switch on subtracting like then minus index. If that is less or equal, actually, then that's bad. Dang, that is quite verbose. Okay, then how do we do that in the switch? Let me just quickly check that. Oh, in the case we say to waffle. Yeah, okay. And there's a pesto body. Well, no. Yeah. So we have this. Then we let me maybe create a constructor for the body, for a body without locals. Oh, look at that. A waffle bodybuilder, after all. Okay, sure. That's nice. Okay, I can just do DAG. Do I have a DAG here? Yeah, fun.day. Oh, nice. Okay. Much more compact, I like that. Yeah, for these, we'll do something similar, except we'll do this one twice. Oh, hang on. Actually, no. This one. Let's say index minus len. I think that's more intuitive. Yeah. So if the index is equal or greater than the length, then we panic. All right. Now that we've checked that, we can actually get something from the array. So what we can do is we just, you know, boom, I guess we just check if we don't have a switch in here. No, we just do. I mean, the weird thing is the array can be. The data can be big. Hang on, but that's okay because we do have a waffle load. Yeah, nice. Where do we get the data from? Well, from the array. From the base pointer. So the array dot member there's waffle member. Is that a thing? Let's see. Yeah. Dot waffle member. So this is array.waffle member at offset 0 with size 8, alignment 8. Then we have the start. That is the member offset 8. Actually, let's extract these in here. Then we have the len, which we already used down here. Okay, alright. So yeah, we load, well, we add the pointer and the start. Yeah, pointer and the start, and then the index. And also 8. Oh, sorry, 16. Yeah, let's move these around. Yeah, we take the pointer, then we skip the reference count and the length. We skip the start fields, and then we skip the index fields, and then we get, yeah, exactly that. Size and alignment. Nice. Oh man. That was quite complicated. Well. Do I need to drop that here? I'm actually not sure. Okay, I'm getting the length of an array. That is simple, at least, because that's just getting the array and the length. And that's it. Nice. Getting a sub-slice from an array. Oh, that is a bit more complicated. So we have an array and a range, which the array has a pointer, a start, and a len. And we also have a range, start and end. Oh, and I think, yeah, the end comes before the start in the memory layout, because E alphabetically comes before S, so end before start. Which means the start is at offset 8. Oh, hang on. The length is at offset 16, just realizing that. Alright. Yeah, cool. And then we return a new array. Which will be quite similar. It will have the array pointer. But then lots of other stuff. Oh, and also the sanity checks. Yeah. Now this would be the original array start. And adding the range start, which is always relative to the current array. And the length will just be waffle sub of range and minus range start. Binds checks. First of all, check that the array length, so the range then that the start is larger or equal to 0, that the that the start is less or equal to the end, and that the array range start plus range len less or equal to array len is. Yeah, let's do waffle body I don't know, waffle body crash and waffle body nothing. Just as constants down here. Or below here. Yeah, sure. Nice. And then here we can just do yeah, switch, and then here this will take you waffle body nothing, waffle body nothing, and waffle body crash. Yeah. Yeah, sure. Let's write that. Why not? Cool. Now we want to check that the range start is larger or equal to 0. So range start is that equal, less, greater. Oh, hang on. Equal, greater, less. Yeah, less is bad. And that the range start is less or equal to the range end. Then we'll just do something like that. And if the end minus the start is greater, we don't do anything. If they're equal, we don't do anything. But if it's less, well, crash. Fair enough. And then down here, we check that when we add, when we subtract from the array len, the addition of the range start and the range end, if the array len is bigger than that, greater, we don't do anything. If it's equal, we don't do anything. If it's less, we crash. Okay, and then here we get the subslice. That makes sense. Nice. Alright, yeah, this is a to-do. I'm fine with that for now. Yeah, okay. Let's see. Waffle load of some layout. Where did I copy that from? I think from the load instruction. Oh yeah, expression.type.memory layout. Yeah, that makes sense. Same here. I think. Yeah. No, we don't need that because we already have an item here. No need to memory layout that. Yeah, oh, that is cool. Yeah, so we do have a waffle, if I got that correctly. If so, by the way, that's gonna stop for today. been doing a lot of programming, so yeah, we have this optimized level. Let's print that because that's easier to understand usually. Well, we can't even print the waffle, so all right. Ooh. Okay, we have a main file. So what that does is it allocates memory. Pretty cool. Hang on, it does what exactly? We have, go to the playground. We have a filled array of 2 elements, 2 numbers, 42. So we add 16 and 2 numbers, so 2 times 8. Very nice. 16, 32. We allocate 32 bytes. Pretty cool. And then we store into that pointer that we've allocated a 1. That's the reference count. Yeah, then adding h to that pointer, we store the int 2. That was the length of the list. And then we store to offset 16 2 times 42. That's this store multiple. That's what that's supposed to be. I think in between these we also need to add new ones. Now that is cool. We store multiple 42s, 2 to be exact, into what this array points to, plus 16. 16 being skipping the reference count and the array length. Oh, that is nice. That is really nice. I like that. Pretty cool. So yeah, store multiple to ground. That is remaining. And I think the reference counting is not correct, because I don't see a single 3 in this code. But I'll get to that at some future point. So see you then. Okay, next step, implementing store multiple in the ground. So currently we can't compile that. I think that should work in, that should happen in here. Yeah. And that's probably going to be similar to store, but even more complicated than this one, which is already quite big. So yay. Let's maybe just copy that and then adjust that. So we want to store multiple. And here's the information of what we want to store. Alright, so the data, we align that to 8 bytes. I mean, sure, we can do that. You know what, let's not do this optimization right now. Let's only simplify things, and then we can make them more complicated later on. So we have the data, which is going to be the value. We also want the number of times that things should be boxed. We need to store that as well. But the number of times also changes quite frequently. So I think that should actually come after the actual data, maybe. I don't know. Hang on, is that even legal? Like switching around the... I think the waffle in the store instruction, for example, these optimizations here, for example, they assume that the pointer is needed or computed before the value. For example, we allow pulling the parameter into the pointer calculation, but not into the value calculation. But that's not what's happening in the ground. That's not what's happening here. Here we first compute the data, compile that to instructions, and only then we compile the pointer. That is incorrect. Yeah. So let's switch that around first of all. All right. Yeah, and this is padding before pointer, and then padding before data. Then we do stuff. Yeah, also let's have even more padding before the actual, you know. Before we do the actual work in here. Oh, just realizing this is, the pointer has a size of 8. So this is already aligned to 8 bytes. Padding before pointer, padding before work. Padding before pointer. then the data, then padding before work. But we also need to skip the pointer. Yeah, because now it's not on top of the stack anymore. So we also need to push that. Push H from stack, pointer start. Yeah, okay. Yeah, so let's copy that, which is the fixed version. Okay, and here we compute the pointer, then we compute the number of times that the value should be copied into the memory. Then we compute the actual data. Then we have more padding. All right. Yeah, and let's maybe remove this for now. You can always add that later. And here this copies a single value into the pointer. That is correct. But basically I need to emit a loop because the number of times is only one time known. So we can't just add a series of instructions that does the correct amount of copying. We need to have a loop in the actual generated ground code. So I think the way that might work is by, well, first keeping basically a cursor, maybe the number of times that we still need to copy that. Yeah, that is fine. And then we basically want to have a switch. Sorry, a jump table. Where we basically check, is the number of times 0? If it is, then that's totally fine. Yeah. Hang on. How do we do that in the switch, though? Like this. Jump table index, yeah. Then we do stack size at start of case, well, yeah, no, don't need to worry about that. Here we have the table, we don't need that. We don't need that because we don't have cases. We just hang on. Yeah, we need to check is the number of times 0. So times builder dot compare 0 with the maybe that. With a number of times. Yeah, so we push the counter, then we compare that to 0, giving us a byte that we then switch over. And then we have a table, and first of all, if it is equal to 0, we will just push and jump to the end. Okay, yeah, we do need end jumps. Yeah. I guess. All right. If it's less, equals and greater. That just does something. If the number of times we want to copy that is greater, then we want to not entirely sure, to be honest. And we want to copy an item there, I believe. Yeah. So we want to basically do this, copying a single item. Let's move that up there. Yeah, we want to push 8 from the stack, the pointer start. We want to push the cursor. And I think I also want to we also need to add the counter, basically. So kind of like builder push 8 from stack, the counter start, then builder push 8, just the size of a single item, which would be store.value.size. Yeah. And then builder.push of builder.null. Yeah. Kind of take the counter, how many times we wanna, like which item we are currently copying. We copy that, we multiply that with the size of a single value. We add that to the original pointer to get an index into where that, into the beginning of where that item is supposed to be stored. Yeah. You can do that outside outside the loop. So value base. Yeah, here we push the pointer and the counter start. We multiply that with the value, we add that to the pointer. Yeah, and then in here we just push that. The base offset of the where the value should be stored. We add the cursor, and then we push a byte from the actual data that we want to copy there, and we store that. True. Yeah. So now back here on the stack, we just have the. Oh, we have a lot of stuff. We have, first of all, the counter. And now the value base thing. So now we pop the value base. And then we I'm not sure. Hang on, we pop the value base, and then we want to add 1 to the counter. And then we are jumping back to the start of the loop. So yeah, let's call it jump table index. Cool. And then if things are less, well, that's not, not valid. So we just crash, I guess. Yeah. All right. Yeah. Then after this whole thing, this is the end. And then for all the end jumps, we patch them. Yeah, we patch the jump table. And then after the loop, we want to pop the counter. Push 8 from stack. Yeah, we push the original pointer. Oh, hang on, no, this doesn't, hang on, this doesn't return anything. Shouldn't. Why does store return something? I don't get that. Yeah, no. I think that's just, nope, that's just a pop. Yeah, same here. Don't need to return anything, we just pop these. I'm pretty sure that this doesn't work because that would be like, this is quite low level code. Okay, we have a jump placeholder. All right. And then we patch that immediately, I guess. This does seem very complex, like very, I think store multiple is quite the high level instruction compared to the other ones. You know, things like add or even malloc and free, these lower to a few bytecode instructions. Sure, load and store, they are a bit more complicated. But store multiple is like a loop and stuff. Not sure how I feel about that. To do figure out. Oh. Yeah. Oh yeah, crash instruction, true. How does that affect the stack? That is actually a good question. I think that just completely invalidates the stack size. Oh, let's say it doesn't affect the stack size. I think it validates it, yeah. Like that. Yeah, so we need to store the stack size. How do we do that in the switch? Yeah, like this. Yeah, sure. Yeah, because those branches, they don't, they don't affect the stack size. Cool. Yeah, that's kind of what I thought. But it will be interesting looking at the ground. Okay, so there's certainly stuff going on. Okay, let's see. So what are we doing? We are creating a filled array. All right. Apparently that means calling the filled array function, I hope. Well, we push a 16. Sure. And then a 2. Then an 8. We multiply 2 times 8. That is 16. Oh yeah, that is the place for the 2 integers. 2 integers. With 16 bytes for the reference count and the length in there. Alright, so we multiply these 16s, we add these into 32 bytes, we push an alignment byte of 8, we allocate 32 bytes with alignment 8. And yeah, we do that in here. That is already pretty cool. Okay, so we're allocating memory for the array. Then we push something. Oh, no, hang on, here. Then we push that pointer again. We push a 1. We push the pointer again, and again, and 0, yeah. Okay, Okay, so this right here is just the original pointer. Then we push the 1 here. Then we store the 1 into the pointer plus 0, aka the reference count of 1 is stored in the first byte of the allocated memory. Okay, that makes sense. And then this, the effect of this here is all popped from the stack. So we're only left with the, oh hang on, we have push, 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 then adding 2 together removes 1, another push, and then storing something. Yeah, there are 2 left. Oh yeah, and these get popped. All right. So now the only thing remaining on the stack is the pointer. Afterwards, we push the pointer again. We push an 8. We add those, okay, to now point to where we want to store the length. So we push a 2, which is the length of the array. Yeah, we push those 8 again and again. Pushing 0, adding 0, okay, I guess. And then the length again, okay, storing that, popping 16. Okay, so now we've stored the, hang on, this stores the reference count, and this stores the length of the array into the memory. Now we're actually copying the data. Phew, that was quite heavy. I'm wondering, can I bring some of that complexity into the waffle, maybe? But I don't know how. I think yeah, that'll probably be fine. All right, so here we push the pointer to the array. We push 16, we add that, okay. That is the base point of where the items begin in memory. We push how many times we still need to, oh no, we still need to copy items. That is 2. We push the item. Then we push the 2 again and the item again. We compare we push the 2 again, okay. We push the what is this? We compare the times. How many times do we need to copy that? We compare that to 0. Yeah, that's going to be greater. So the jump table containing equals greater and less will just jump here and push 8 from the stack. let's see, we skip the, I mean, this was consumed from this one. Yeah, this is the counter. The counter is still on the stack. The data is on the stack. And yeah, the counter is on the stack again. And before that was the base address of the values. So we push that base address. Then we push the counter. Yeah, we multiply that counter by 8. We add that to the base address. Then we push some data, probably. Add 0, I mean, sure. And then we store a byte there. I don't know. First of all, the counter is kind of serving two purposes here. I think we actually want to counter that, yeah, that just is 0 in the beginning. Makes sense. And then here we need to compare that with the pointer oh, hang on, this is the loop start, by the way. Yeah, we don't want to immediately jump to the jump table. We want to jump to the loop start. All right. In here we need to compare that counter to the length, the number of times that we want to store that. I'm not sure about the order of these. I think sub really subtracts the first one from the second one. So counter minus times. And on counter minus times, that means I'm not sure, hang on. Counter minus times. Yeah, if that is less, things are fine. If the counter is greater, then we want to break. So basically need to move stuff around here. Yeah, if they are equal, counter on times, and counter on times. If they are equal, yeah, we want to exit. That makes sense. If they are counter minus times. If it's at some point, if like as long as the counter is less than the times thing, that is negative, and greater should actually never happen. So this, let's move this in here, and this up there. Yeah. And I think we can also simplify stuff a bit by not pushing stuff to the table of where to jump, but instead equals case is builder instructions.n. I mean, for the equals case, we immediately want to jump to the end. Well, I'm just going to prototype stuff. So the greater case is here, and the less case is here. Yeah, so rather than pushing stuff to a table, we just store these, and then in here we can just patch the jump table using table of the equals case, the less and greater case, and the less case. Now comes the cool stuff. Well, let's maybe put new ones in there, because I think I can even simplify this. The equals case really just wants to jump to the end. So we have these end jumps for that. And then in here we patch those with the end. So we can just replace that with end. You know, if these are equal, then we'll just jump to the end directly. No need for this entire case. No need for end jumps. No need to iterate over them down here. Yeah. Let's maybe say counter equals. Yeah. Then the greater case, I mean, this is like, this should never happen, so I think I can also just remove that. And then the only case remaining is the last case. Okay, and let's name this patch because that's the terminology that we use everywhere else. All right. Yeah, that seems cleaner. Very cool. All right, so is this needed though? Because this loop has no effect on the stack length. That's in fact part of the loop invariant that's the case. I mean, we can put an assert in there. Yeah, sure. But then let's do that at the start of the loop. Nice. All right. Whew. I mean, this is weird that we have to create a placeholder. Let's simplify that as well. Yeah, jump placeholder and patch jump if we already know where to jump. We can just do that directly. Yeah. Okay. Slowly wrangling that complexity. I know. Mm-hmm. Mm-hmm. Yeah, that's great. And then let's maybe add this optimization because I think now I feel a bit more comfortable doing that, you know. Value start is a really You know what, let's maybe add a couple of stack comments in here. So we have padding, then we have the pointer. Then we have the amount of times. Then we have the data. Then we have padding. Then we have the counter. All right, so then the loop starts. Yeah, and here the stack is still exactly that. Here we pushed two numbers, we subtracted them, leaving us with a byte, with 8 bytes, an integer. We compare that to 0, giving us only a single byte, and then jump table placeholder. The jump table consumes that byte. All right. Let's call that just value pointer, because of course it's the base. Hang on. We have the counter in here. We have the loop start. Yeah. I think in here we need to also add 16. Oh, hang on. No, that's already done in the waffle. Yeah, that makes sense. All right. Yeah, so we have that. And then if that's the case, we push the value pointer another time. We push the cursor. We push, we add them together. Okay. We push 8 from the stack from the data start plus cursor. Yeah, and this is only done if the data, well, you know, take care of alignment. All right. I guess that's nice. Yeah. We allocate memory. How is that even happening? You know, adding 0 to stuff. Oh, I see. Because this is like a push followed by an add. And if that push is with that's maybe built, yeah, push macro instructions that actually consist of multiple instructions. Exactly. that should just check if the immediate is not 0. Only then this pushes that number and then calls at 8. Otherwise it doesn't do anything. So then we should be able to just do that. And for the case where the cursor is 0, this will actually not do anything, which is pretty amazing. Yeah, and here push and add, that is just an add. Also, like, a lot of code just gets simpler using that. I think also in here, yeah. For the first iteration, that's just not going to omit any instructions. All right, let's see. All right, we allocate 32 bytes. We push that pointer. We push now this multiplies these, this adds those. Oh yeah, this pushes that number again. This is just putting a byte. Okay, we only have the address on the stack. Then we push that address again. Okay, we have the pointer. We push a reference count, oh I see, of 1. Then we push, yeah, we kind of store that in there. How is that? I think we can make that more efficient. Why not storing that and then popping stuff, but just, you know. Oh, I think in the waffle. Yeah, here we store something into that pointer. Fair enough. But why does that have the oh, I see. Yeah. So basically, if we are storing something, yeah, we are computing the entire pointer, makes sense. And then the value also makes sense. And then we are copying the value by, piece by piece, pushing a pointer, a part of the data value that we want to push, and then storing that. We can simplify that. We can say if the value is 1 byte or 8 bytes, then we can just emit a store instruction and we're done. So if store.value.size is 8, oh, let's say 1, then we just do, I mean, we already have the pointer on the stack. We already have the single byte on the stack. So we can just push a store 1. Yeah. All right. yeah, else if store value the size is 8, then we just do a builder store 8, else do it piece by piece. And store data piece by piece. Nice. Can we do the same tactic down here? I don't think so, because we don't know the number of times that we want to store something. Yeah. Okay, I think that is a bit shorter. 64, before that was, yeah, 52. Nice. And these tiny optimizations, they make the code a bit more readable here. So here we just push the pointer to the stack. We push a 1 and we store that 1, that's the reference count. Then we push a pointer to the stack, we add 8. And then we push a 2 and store that. That's the length of the array. Then we push the pointer to the stack, we add 16. And now things become interesting. Now we have this times variable here. We have the the value to be stored there. And a cursor. Nice. We push that cursor and then we skip, 8, 16, 24. We push the number of times that we want to copy that thing. We subtract them. Yeah, we compare them. Compare that to 0. Basically checking if this one is larger than this one. And then we jump on the result. So is our cursor larger than 0? Hang on, I think it's the number of times that we want to copy that. How does that compare to the counter that we have? If that's less or the same, we just jump to the end. Otherwise, we just jump here, where we just jump, push 8 from stack. We yeah, we've consumed these. So 24 skips 8, 16, 24. Okay, and before that was the pointer. So in this loop iteration, we store the pointer and the cursor multiplied by 8. We add those to get the base offset of the current value. Oh, this is weird. And we add those, and then we do basically this part right here. It's 22. Yeah, the cursor is 0 apparently, that makes sense. And then we do push 8 from stack of the data start plus the cursor. Yeah. How is that 22 though? That doesn't make any sense. You know what, let's maybe print stuff in here. Yeah, let's say value pointer is a 26. That is weird. That is a really odd number. Can we print the same for counter? Oh no. Yeah, this has to be the stack size. Not the instruction length. Makes sense. Ooh, it produced the correct output. What? That is cool. That is really cool. Okay, let's see. We push 8 from the stack, the 24. We do that. Okay, we calculate the base offset. And then we do this. We push the base offset again, and we just store. Yeah, we push the value, and then we just store that and pop 8. Yeah, then we add 1 to the counter. Yeah, we add that, and then we jump back to the start of the loop. Ooh, 21, which is here. Okay, that is pretty cool. That is pretty cool. And at some point we just jump out of the loop and we pop stuff. We can simplify this here by just similar to what we did up here, by special casing that for 1 and 8. Yeah, start value dot size. If that's 0, then we'll just, if that's 1, we need to push the item. Same here. And that makes sense because we don't know the number of times that we want to store the item. So it may be that we just, so it may just be that we need to copy the item. There is no way around that. We can't just let the store consume the item, because if we have multiple iterations of this loop. All right. 46 instructions. Oh, well, stuff is wrong. That's not good. Hang on, here we calculate the pointer. And then what we do in here is we push that pointer again to the stack. We add 8 to that. Sure. We push the data from the stack and we store that. Still we're popping 8. Why is that? I mean, yeah, okay, that makes sense. Yeah. Like after we're done with this, we just pop the original value pointer. But here, oh, I see. Yeah, that makes sense. Yeah, here we just push the value and then we directly consume that value pointer. Oh, this is, yeah, 44, a bit shorter. This is nice. Really nice, actually. Whoa. Yeah. I guess that's cool. What else? Let's try something a bit more complicated. Let's say we have a filled array, but with length 10, maybe. Yeah, that works. Just allocate more memory. And critically, the same number of instructions. Because the only difference is this number up here. That is cool. And well, down here. Ah, because that was inline several times. I see. Yeah. In here and also in here. But still. Ah, that is nice. That is super cool. Alright. Yeah, let me maybe take a break. I am wondering, why isn't Zig complaining about memory not being freed? I think it should be doing that. Yeah, let's look at the... Oh. Yeah, just at the Zig VM, which is in here, I believe. Yeah, we're freeing the stack, sure. But the heap... we have this run function that has a heap that it initializes with the allocator that we pass to the run function, and that one has this malloc function which calls this one, which allocates memory, and a free function. And free is only called from the free instruction, which is somewhere here. Yeah, we don't free memory at the end of the when we return or something. No. No, here we just immediately return. Yeah, here we free the stack that the program returns. That makes sense. And reprint those bytes. But up here, don't we have some sort of... Yeah, this one right here, where we say this should be de-initted. We should leak memory, I think, because we allocate these bytes without freeing them. I don't quite get that. I don't get that at all. I mean, if we just allocate memory manually, does that get recognized? Let's see. Yeah, a bunch of tests. Okay, fair enough. Here, like malloc. Yeah, we do this. The program runs, and let's say we also allocate, I don't know, 10 U8s. Yeah, that is true. Oh. Is it like a debug build versus release build thing? Maybe let's just try to build that in debug build and see if... Yeah, okay. Yeah, I see. Yeah, I'm gonna go with debug builds for now, because it's not like I'm running huge programs that need the performance. Alright. So we are leaking memory. Let's not do that. Let's... I mean, the waffle, I think, is already wrong. Yeah, because here we store something in the array. Yeah, here we call the array.len function, giving the ownership of the array into the function. totally makes sense. The main function is doing everything correctly. And here we're passing the array, nice, which is 8 bytes. Oh yeah, and the array actually represents memory range from 0 to 10. Oh, that is clean. That's clean. Alright, and we pass that into this function, which just does nothing. I mean, it gets the 10 out of that tuple at offset 16, but that's not enough. It should also free the array. So in the something to waffle, I think we need to do a bit more. We have compare ins, we have filled array, which works pretty nice. And then we do array get and array set and len. I think len is actually the the most not interesting one, but the a very simple implementation currently that we can fix. So yeah, we get the member here, but we also need to decrement the reference count of the array. So similar to how we, treat, what is it, dupe drop things here. Yeah, we basically need to do that. When dropping, and when getting the length of an array, because that should also drop the array. Yeah, the pointer is, well, basically just that. Array.waffle member at offset 0, size 8, alignment 8, and then we subtract, waffle sub, waffle, we load that pointer, 8 bytes from that pointer, that's the reference count, we subtract 1, and then we store that reference count again into the pointer. And then if the new reference count is 0, we also want to free that. Oh, and free the individual items. I didn't even think of that. Well, I think we don't have enough information in the pesto. Yeah. To free the array, hang on. I mean, this is a function that is specialized for ints. Yeah, no, I'm afraid we need to put the array somewhere further to the front of the compilation pipeline. But I'm gonna commit this first, because this is a somewhat working version. So let's kind of go through that. Oh. Yeah, I think these array functions, they are the first built-in functions that operate on heap allocated data structures. That's why this is something new that I haven't encountered yet. Yeah. I was just wondering, like, what do we do for, I don't know, ints or something? Mm-hmm. Yeah, that's work in progress for sure. Okay. So, it does seem kind of wrong that, these are kind of instructions similar to adding ins and comparing ins. Like this, these feel way more complicated. Getting something from an array means you're extracting the item there, copying a bunch of memory. If the reference count of the array reaches 0 in that point, because we take ownership of that and we need to decrement that, also free the array, which means freeing the individual items in the array, and like there is a lot of stuff that's going on there. It's completely different order of complexity than these other instructions. What the hell? Yeah, so I think I need to kind of decide in which compiler stage I de-sugar that. So let's just print a bunch of compiler stages, I guess, and just see where that might fit in. Taking a long time by now. Well, all right. So in the yogurt, yeah, I think here it's fine that array len is a built-in. Or is it? I mean, the yogurt is basically just a type-checked version of the egg. A type-checked and monomorphized version. So yeah, it is fine that array len is a function that seems reasonable. But then in the pudding, we already have these kind of drop instructions, which work on arrays here. Okay, so that's fine. We basically like drop an array, for example. Okay, still, we still have enough type information, enough. Like this seems coherent, the abstraction level, I think. In the pesto, though, things kind of fall apart. Here we have array len with this type. It only has one argument, and that is this one, an array with a start, an end, and a buffer. Yeah, we get that, and then we call array len on that. This seems weird because we already have, the end. And also, why are arrays really represented like that? I thought they had a length, not an end. Let's see, something to pesto, and here types, I guess. Yeah, no, there should be a len, I believe. Yeah. So I think while going to the pesto, we actually want to simplify stuff. Yeah. And I think at this point we also want to handle some of the built-in functions and desugar them. And not just map every instruction to a call to some instruction. But instead, switch on the instruction. Yeah, if it's add-ins, then that just becomes an add-ins instruction. Yeah, for most of these, this will just be the identity mapping. But not for all of them. And these are fine as to-dos. Yeah, these will all be possible cases. And these first ones will also directly map to themselves. But then, for example, ArrayLen, I think, really that shouldn't be some sort of built-in structure. That should just... oh yeah, that also makes sense, because arrays are desugared into structs that point to some buffer. Yeah, okay. So ArrayLen really just does yeah, it drops the argument. Hang on, argstock@0 is the array. And then it drops array dot, what is it? Builder, no, array dot. Hang on, in the pesto. And dupes and drops, they operate on pointers, I believe. Or on types, I'm not sure. I think on types. Yeah. So we could, for example, add a function, push array drop, something like that, with the buffer. That is like pesto member or something. Yeah. Pesto up.member. Yeah, that is the buffer pointer. Getting the buffer from there, that's a pointer. And then we do push array drop, or the buffer drop. Of the type. Yeah, we drop the underlying buffer and then we just do pesto up dot another member expression, getting the name. Instead of having something like that. Putting instruction is not an enum. but the instruction. Sure. Let's do that. Yeah, push buffer drop, which for now is just gonna do nothing. But I think it makes sense. You know, we have these compile functions for dupes and drops, and we special case them for closures. We also have compile closure free fun. Well, not the dupe and drop, but you know, you get the point. So I think it's just consistent if we also have buffers, if we special case them here. I don't know, just nothing. Pesto up dot. Like an empty struct or something. Yeah. Just a placeholder for now to see whether that's even the correct way to desugar things. Yeah. Okay. A pesto op. Oh, and that doesn't have an expression. Sure. Mm-hmm. Yeah, I guess just return that. Or just inline that in every case. I think that's basically that's the cleaner version anyways. Yeah. Let's do that. Let's just remove this, de-indent that entire thing. Remove this and instead move that into every case. Because then some of the cases don't need to do early returns, they can just all evaluate to something sensible. Plus it's not really a lot of code. Okay. I have to add here endless indentation, all that good stuff. Get to that. Yeah, then here we don't need to return. Also quite nice. Look at that. Cool. Yeah, and here we still have the same. I mean, yeah, we still do array returns, but I'll change that. Yeah, and return that. Let's see. Hang on. Okay. One that I missed. Yeah. Isn't that just nothing? Pesto nothing? Yeah. Oh, but of a different type. Yeah, I guess. Oh, there's a yogurt type. Ah, I see. Yeah, we can just ignore that type there. For closure, that, getting a closure, something like that. Right, so in the instruction case, we also need to wrap this. Cool. Then, yeah, that compiles. So here we go. Yeah, this will crash. I know. I'm just interested in how, like, what does the len fun look like in the pesto. The length function just does, gets the array, okay, then it gets the buffer. It does nothing, and then it gets the length out of that buffer, out of the array. Yeah, that works. Nice. And this is the place where we can insert code for dropping, like freeing the buffer, basically. So, freeing, like dropping a buffer. I mean, this is really just like drop buffer, I guess. All right, yeah, we just, we have a pointer. This is a pointer to the buffer. mapping a buffer pointer with type. Let's just see what that prints and go from there. Okay, yeah, sure. Waffle here, dropping a buffer 3 with type. So 3 is correct, that's the buffer here. But then type. Hang on, we call that down here. And here. Or type of array. Huh. Fun is a pudding fun. What does that look like in the pudding? We have this right here. We have an array. Oh, I see. Then we create a type. We create a never. Dropping the type. Okay, sure. Then we have this instruction ArrayList. Type, somehow it gets to that. Oh, I see, because the array has already the mapping applied, I think. Ah, that makes sense. Yeah, let's move that down here maybe. And in here just do instructions .args get 0. Yeah. We have the buffer. Yeah, okay, so let's get the arguments out of there. We can do that, and then just never mind. That's fine. Instruction args. And then we get the member of, the compiled array from the mapping. Yeah, that's a pointer. Then we push drop from the type of the original array ID. Yeah, okay. And then we build that off the array from the mapping. Let's see. We have the pudding, sure. We have the pesto, yeah. Oh yeah, dropping a buffer 3 with type ArrayInt. That is correct. Nice. Yeah, and I think here I'll just need to think about what to do. I think let's get the array out of there. And let's extract the item type. This is, we know that this is an array, and that should give us the item type. Maybe not, there is no array. Oh, there it is. Okay. Yeah, dropping a buffer 3 with type int. That's pretty nice. All right, so yeah, basically I just want to do this. Well, kind of this. Compile drop buffer fun of a buffer of that type, and I want to call that with the ID, with the pointer. That returns pesto nothing type. Yeah, and that doesn't exist yet. That's true. And then we have dupe, we have drop. Dang, that's complicated. We have closure free fun. And we have compile drop fun with a yogurt type and pesto, and that should do something similar to this drop fun, I guess. So drop buffer of that. Dropping a buffer of ints. Yeah, if that's already there, we just return, sure. Then pesto funds, put an uninitialized thing in there. Yeah, we create a DAG and a builder. Yeah, and it doesn't so much depend on the type here. Not really. I think we just want to iterate over the items basically, and then drop them. but also load them and do that. Kind of switch on that. Well, come to think of it, it's kind of similar to a closure, I guess. And that a buffer is always allocated on the heap. So let's copy that code. Okay, so the first thing we do is we drop the pointer, the parameter to this function. Yeah. Oh no, hang on. Am I just editing the original? Yeah. Sorry about that. Let's not do that. Let's instead edit this correct function. Yeah. So we drop the parameter, which is the buffer. We compare the reference count to 0, get back an ordering. And then we switch on that ordering. Yeah, less doesn't really occur, greater. We don't need to do anything. Equal though is interesting. Here we need to drop the individual items and then drop the entire buffer itself and free the buffer then. Yeah, so the outer builder is the builder, okay. And here we have a builder for this case. Sure. Not sure what this does. Probably the argument, maybe. Ah yeah, makes sense. And then we have the value here. Let me think. Okay, I think we need to drop the items here. And then we free the original buffer. Yeah, that makes sense. And then this, we don't care about that. We can just remove that. What's going on here? We pesto free, I think. We need to create something new there. Yeah, in the pesto we have new that allocates a single value on the heap. We have load, which loads value from the heap, and we have free. we need some sort of new buffer and free buffer. Load buffer, not really. Let's first add the free, I guess. Exactly. Yeah, with a pointer to the buffer and then the type. Exactly. And then in here we can do free buffer. Free the buffer, please. The type is just our type. Yeah. And dropping the items, that actually requires kind of iterating over the buffer, or like iteration is done in functional style, just recursion. So I think we'll actually have a different, compile and drop buffer items fun. And that accepts a struct accepts aggregate with pointer and cursor, maybe. Yeah. Perfect. So this could then, first of all, check if the cursor is done. Similar to what we do here, by the way. And we need a new function, so we need, sure. Drop buffer items of int, for example. And then here we say the new ref count is going to be the, nope, not this one. Instead, we'll just get the pointer, which will be the builder.push pesto up.member of the builder param. That will be a pointer, and we'll have a len, which will load, that we need to load that from memory. Yeah, but we do have a cursor, which is a different member. Oh, I think this also needs more stuff, which totally makes sense. Let's see, in the pesto, and in here, I guess. Yeah, something like like this. So taking the builder param member. Oh yeah, this, oh, probably need to adjust that here as well. Yeah, no, this just accepts a pesto type pointer. And this down here accepts pesto type.struct with two fields. A pointer. It's going to be pesto type pointer, and a cursor. So it's going to be a pesto type int. Yeah, and then we'll get the pointer out of there. We'll get the cursor out of there. And we'll load the length, which will be, well, pretty much that. We load from, yeah, we load the pointer of the type int. Oh, hang on, that's the reference count. Len pointer. Yeah, let's do it. This buffer pointer is that. Len pointer is with pesto op dot call instruction. Yeah, calling the instruction. Pesto call instruction with an instruction and arguments. Now we're calling the add instruction with arguments, well, the buffer pointer and 8, which we'll also create here. Yeah. Okay, and then from that len pointer, we load an integer, the length. Then we compare that length with, oh hang on, not the, oh, yeah, we do compare the, nothing with 0. Ah yeah, we compare the cursor with the len. That makes sense. All right. And then we, yeah, that returns that. We then switch on that ordering, I think. Yeah. So we need a switch. Oh, this is so much fun. Quite verbose, to be honest, but you know what, let me add it to do. Create pesto builder. This is the buffer fun, this is the buffer items fun. yeah, if the cursor is less than the length, yeah, then we need to do something. We need to drop the item. So what we'll do is we'll get the item, hang on, the item pointer first of all. The items pointer. Hang on, the buffer pointer plus 16 basically. So we need to create a 16. Hang on. Yeah. And then we add those. Then the item offset is the size of a single item. Luckily we do have the type, and I think we can just do type dot size or something like that, maybe. Oh. That depends on the memory layout, which we don't yet have in the Pesto. We do that in the waffle. I mean, we could just add a specialized instruction for that. Yeah. Something like Pesto or buffer offset, something like that, where we just pass in something. Not buffer, but stride offset is a nice way of putting that, I think. Yeah, no, like that doesn't exist, but basically taking the item type and taking the number of like a Pesto, like an ID, that an index of the item. Yeah. So there's like the item offset, the index being the cursor. Yeah, and then we can add those, the items pointer and the item offset. To get a pointer that points to the exact item. Yeah, then we can load that item. And we can drop the item. Whew. That was quite the code. Yeah. Then we can. Hang on, what else do we have? We have this equal thing. Yeah, if we reach the end of the list, hang on. The comment goes here. Never runs in practice. Cursor is always less or equal to n. Yeah, if it's equal, then we just want to not do anything. Oh, I see. Because in here we also want to call ourselves recursively. Yeah. So let's first do that, I guess. Yeah, in here let's say we call drop buffer fun. Yeah, we need to drop the items. Pesto call of this one right here. Compile drop buffer items fun. Yeah. Perfect. And we call that not just with the value, which should just be the pointer, I guess. All right. So, yeah, and here we need to do something. First of all, let's kind of divide that up. And then the arguments are going to be a pesto struct, I guess. Oh yeah, a pesto struct of that type. Perfect. And the struct also needs a pointer. which is going to be the buffer pointer, and it needs a cursor, which will be 0. And we already have 0 in here. Yeah, we do. All right. Yeah, then we call that with the arguments. Clean. Honestly, that's pretty clean. Yeah, and then in here, we can just calculate the item pointer. That's basically what that is. Then we free the item. And then we call ourselves recursively in a very similar way to what we did up here. Yeah, the buffer pointer stays the same. The cursor is going to be cursor plus 1. Just quick 1. Sure. Just going to push a 1. Then the next cursor will be, well, an addition. Of the cursor and 1. Nice. Then we'll have the arguments with the pointer and the next cursor. And then we'll call ourselves recursively with those arguments. Clean. That is quite a bit of code. Call instruction. And that returns us the add-ins instruction returns a pesto type and a pointer. A pointer is what we want in that case. Could unify those. Let's add it to 2. Alright, then pesto stride offset. Doesn't exist. Yeah, that is indeed true. So we want a new pesto up. Stride offset. Yeah, calculate the offset of a value in a memory region, I guess. Memory region. Yeah, And then we do pesto stride offset. That will have a type. And it will have the index. I think they are the other way around in the other one. Calculate the offset of a value in a memory slice where multiple values of that same type are next to each other. Cool. Yeah. And then pesto op.stride offset. Oh yeah, that has that. Let's see. Yeah, that needs pesto type. To pesto, I think. Or compile. Okay. Yeah, adding ints, giving us a pointer, let's say. Yeah, same thing. And yeah, now I copied the add-ins several times. So yeah, semantically that's more of an int. So we have type.compile, that doesn't exist. We only have to pesto. When the printing, that's pretty cool. Yeah, printing in here. We have a couple of new pesto operations. We have free buffer. We have, oh yeah, let's maybe call that free buffer. And we have stride offset. And the index. These definitions have the same name, but arguments don't match. We have free buffer. Call this one pesto free. Oh, a pesto free buffer has, what does it have? A type, maybe? Yeah, pointer and type. Sure. You don't handle that in the next compiler stage. That is very true. That is true. I do think maybe I'll replace this with like stride size off. That would be nice. Yeah, let's do that. And then it just accepts a type. And the multiplication can already be desugared here. That's nice. So we do have stride size off. pesto type. Way easier to explain as well. The stride size of a type. Nice. Calculate the stride size of a type. I could just remove the off. Yeah. Alright. And then in here we can't use the offset. Yeah, but instead we'll use the stride size. It's gonna be builder.push pesto up dot stride size of the type. And that is an int. Yeah, and then the item offset is just, well, calling the multiply function. With the stride size and the cursor. Cool. Yeah, pesto to waffle things don't work yet, so let's just comment out these later compiler stages. Yeah, just print the pesto and be done with it. Oh, it compiles. That's nice. Yeah, okay, that's expected. Okay, so con instruction filled array. Okay, that is currently an instruction. We may simplify that later on. And then we create an array. And we put that, that creates an array, and then we put that into this. We call the ArrayLen function with that. That's pretty cool. Which is up here. It has this, it gets the underlying buffer, it drops the buffer, and then it returns the length of the array. Dropping a buffer of ints. Very nice. Well, decrements the pointer, ref count. It checks if that is 0 by calling compare ints with that and 0. And it switches on the new ref count if that is less than 0. Oh, that's not possible, it's greater, we don't do anything. If it's equal though, the ref count is 0. Now we need to, well, we build up this struct containing a pointer to the buffer and a cursor, which is this 0. And then we call drop. Buffer items of int using that struct. And then finally we free the buffer. That is nice. That's really nice. So quite cool. Then yeah, this is dropping buffer items of int. And that just gets the pointer, gets the cursor out of there. It adds 8 to the buffer, loads that. Oh, I see, that's the length, I guess. Yeah. I don't know about that. I think this kind of mixes some abstractions here. Previously, we just had a simple kind of memory model in the pesto. You can just create a new, have this new instruction to allocate something on the heap. It transparently has a ref count. You don't need to worry about that when loading or freeing something. You don't calculate with pointers here, you just have pointers. And you can so you can just load a pointer, loading the entire item. You can free that. But apart from that, items in memory are immutable. And with buffers and arrays, the point is kind of to not do that. The point is to care about the reference count and kind of check, oh, is the reference count 1, then we'll just mutate items in place, for example. So maybe I'll need to add reference counts. You're kind of already overwriting memory items, overwriting buffer items kind of requires this yeah, that requires some kind of store instruction. Making the data mutable after all. It's just I don't like. I'm fine, I think, with giving up this kind of immutableness at this compiler point, and at this point in the compiler pipeline, because we already have reference counts, so we can, we already care about, freeing memory when it's no longer used and duping and dropping things. So adding something like, hey, please replace this thing, replace this value with something else that should be doable. But I don't like that we calculate with pointers at this point already. I think maybe the buffer type should be kind of built in, and there should be some sort of new buffer that, let's maybe write that down, some sort of new buffer with pesto new buffer. That knows the type. And the size, the length. Sorry, not an int, but an ID. That's an ID reference to another pesto expression, because the length only has to be runtime known. So that's for creating a new buffer, kind of. And then have stuff for loading an item. From a buffer. Pesto. But then also store buffer item. And finally free buffer. Yeah, and not have this in here, because pointer doing pointer arithmetic, that is really against the on a completely different level than the other abstractions in this compiler stage. I think it's fine if buffers are somewhat of a built-in thing here. Yeah, so we have new buffer, load buffer item, the buffer has a type, the item has an index, nice. Now we have store buffer item, which also takes an item, and then we have free buffer. Yeah, that's it. I mean, this can just be the pointer. So maybe I don't need to unify these because it, we don't do any pointer arithmetic at this point. So. Mm-hmm. Yeah, and let's call this type an item type, just to be totally on your nose like this is. That's obvious what this is doing. All right. Cool. All right. Yeah, I like that. Yeah, I'll not implement that now, but sometime else. Okay, I figured out what I want to do first, and that is refactor the pesto builder. because, I mean, a lot of these, pushing stuff to the pesto can be radically simplified. These pesto, there was so much noise in here, pushing a pesto op.member with a pesto member. Like, this could just be a function, basically. And also int, like pesto op.int with a number, and then of the type pesto type.int. If we just had a function like builder.int that takes an 8, that would be so much more readable. Yeah, so I think the first step is adjusting the builder, adding functions there for every operation that I support. Functions that just take the necessary arguments that you need to construct the operations. For example, for ints, that's just the number, but for members, that may be the auth, the name, and also the type, because you don't know the type of the member. Yeah. And also, I think I'll put the builder into its own file. Currently, constructing pesto is this kind of weird extra thing on top of the kind of intrinsic pesto writing stuff. Constructing pesto is going to go into a file similar to what we do for the ground. We have this builder file that contains the builder, and then functions for every single instruction that we might want to emit that just pushes the instruction. And I'm going to do something similar for the pesto. Also, it's quite late, so I'll try not to talk too much and just program this kind of relaxing way. There's just a lot of refactoring, manual work, kind of thinking what are nice functions there. Right. The param doesn't have a function because there only exists a single param per builder that automatically gets put there in the constructor. Fair enough. rename this. Dupe and drop are things that act on values. They decrement the reference count, they check if that's 0. If it is, then they just free the values. And dupe and drop, they only work on inc and dec. These will only work on pointers, and they only increment and decrement the reference count. They don't free anything. Yeah, it's just very, very simple. Okay, so that is way shorter. There was like 400 something lines. Yeah, and I mean that's really, really nice. Some of the operations I might even figure out types. Like for the struct, for example. Let's see. I think in here there are some places. Here for example. Here this is something of the type pass to type pointer. This one right here. The cursor is 0 of the type pass to type int. So the struct function could basically look up these IDs and build the type. And maybe let's go through this from the beginning. Yeah, there's just a dupe function, no creation of a struct. Same here. Yeah, this was that. Yeah, here we provide a type. That makes sense. Yeah, here those could be figured out. And similar for member, because members always operate on structs. So if we know that the type of this is this one right here, struct type, with, you know, a pointer and a cursor, then we could just, you know, and the pointer is a pointer, the cursor is an int, then in these member expressions we don't need to pass the type in here. We can figure that out, I think. Let's try that. For the member, we also don't need the type, I believe, because we can just look that. I mean, I'm wondering, here we extend the field. You know, we take the struct type, we extend that one level, then we unwrap that. Ah yeah, that makes sense for the dupe, because this compiles a dupe fund, which maybe, you know, there's maybe a recursive type and stuff like that. But for the member, we don't need that. Oh. Ah, yeah. No, that makes sense. The type, like, the type is compiled to an empty struct, so that's correct. It's like almost, you know, reasonable. Crazy.
That probably won't compile.
But I think I'm gonna stop there for today. Yeah. I mean, maybe some small stuff. But really, I'm satisfied. The code is really coming together now.
Alright, yeah.
Compiles, show there are to-dos and things are not working yet, but still. Oh. Well, the pesto actually compiles. Here's the pesto. Yo. We now have an ArrayLen function that drops the buffer. Fair enough. And then returns the length. We have drop buffer, which, well, takes a pointer, then it decrements the reference count of that pointer as 0. It calls compare the ints, boom. It switches on that. If it's less, we don't care. If it's greater, we don't care. If that is equal to 0, the reference count is equal to 0 of the buffer. And then we create the struct of pointer and cursor. We call drop buffer items of int. And then we call free the buffer of int. This one. Boom. Drop buffer items. Just iterates over the buffer. So it does. That's the length of the buffer. Yeah, then we call the instruction compare ints. Yeah, comparing the cursor and the buffer length. If they're equal or greater, we don't do anything. If the cursor is less than that, then we load the item from the buffer. At the index of the cursor, there's an int, because the buffer contains ints. Then we drop that int. Boom. Then we add what do? We call add ints. Yeah, makes sense. Of the cursor and 1 to get the next cursor. We build up the struct, we call ourselves recursively with that new struct with cursor being increased by 1. Oh, that is pretty nice. Yo. Yeah, here we call the instruction filled array. I need to fix that. That should instead just create a new buffer and then iterate over that, fill items in there. Alright, yeah, cool. Pretty cool actually. Yeah. Making progress.